This question features a mammoth paragraph of about 200 words, but that's not going to stop us. The original question comes with the diagram, but as an exercise, I'm going to draw it as I go along in case the question doesn't. So a small ball has a mass 2.5 kilograms and it's on a rough horizontal table. So I'm going to draw a horizontal table like this. I'm going to draw the small ball A here, label it A, and I'm going to draw its mass here, so 2.5, and I'm going to do G because then that's its weight, not its mass. Given that the table is also rough, I'm going to add these lines just to remind me. The ball is attached to one end of a string. Okay, I'll draw a string on like this. Bit of a long paragraph. It passes over a pulley, so I'm going to draw a pulley. That's the other end. It passes over that, and it's attached to another ball, a small ball B, that's hanging down freely below the pulley. So I'm going to continue that string down and draw B below. And I'm going to add on the weight of B. So the mass is 1.5, so the weight is 1.5 G. Just like this. And it also tells us that it's hanging above the ground 1 meter. So I'll just add this onto the diagram as well. Like this, and then just drawing the floor here. Next, it tells us that the system is released from rest and the string is taut. There's nothing we can really do from that diagram other than know that really being released from rest is quite crucial for parts of the question later on. The resistance, it tells us, because it's rough, the resistance is 12.7, and it tells us it's a constant magnitude, so that's not going to change throughout the question. Also tells us that ball B reaches the floor before A reaches the pulley. That's just so that A doesn't hit it before B even reaches the ground. Finally, some assumptions. The ball are particles. The string is light and inextensible. The pulley is modelled as being smooth and small, and the acceleration is 9.8, but we already know those facts. Those are included in every question. On the diagram, I've also added the tensions. Remember, tension always goes away from the object. So to answer part A, I write down the equation of motion. We're going to use F equals ma, and F here is the resultant force. So it's movement in the direction of motion. The direction of motion is towards the right because A is going to be pulled by particle B, and it's subtract the motion to the left, motion away. So T going forward, 12.7 going backwards, and M is 2.5, and A is just A. For part A double I, it's this very similar thing. F equals ma is the way to go. Force is in the direction of motion. Which way is it going to go? It's going to come down. It's going to fall down. So in the direction of motion, the force is 1.5 g. Subtract the forces going opposite that, which is t. That still equals ma. The only difference is this time the m is 1.5. Now in the question, it's the word inextensible, which tells us that these two accelerations are the same. And the fact that the pulley is smooth tells us that the tensions are the same. So that's why I've not chosen a different letter. For part B, this is just simultaneous equations. If I label these equations 1 and 2, then you'll notice that if we add 1 plus 2, then the t and the minus t will cancel each other out. And we'll be left with 1.5g minus 12.7, and then 2.5a plus 1.5a is going to be 4a. That tells us that a is going to be equal to a quarter of whatever 1.5g minus 12.7 is. So I've popped that in here. Could probably work it out by hand. We get a half. What a lovely answer. Almost makes me feel like we've done something wrong when it's such a nice answer. And that's part B done. For part C, we are asked to use the model, of course. What else would we use? Find the time it takes for B to reach the floor. Because we have an acceleration from part B, and because B is moving down, this is going to be a Suvat equation. It's going to be 1D Suvat because it's in one direction. You'll see 2D Suvat later on in A2 maths. So set out my equations. What do we have? So A we know is 0.5, and that's going down. S is 1 meter, and again that's going down. Make sure it's the same direction. You know from before, from the large question above, that it's all starting from rest, so it's going to be 0 there, and time is what we're looking for. So if you know your equations, or if you have them in front of you, you know S equals ut plus 1/2 at squared is the one that we're going to use. Use 0, plug it in, 1/2 times 0.5 t squared. That's going to be 0, and we're going to get 1/2 times 0.5, which is 1/4 t squared. And then we're going to rearrange. So 1 is equal to 1/4 t squared, and we can rearrange this to get 4 is equal to t squared, which means that t is equal to, well, technically plus or minus 2, but we're never going to have a negative time. So t is equal to 2 seconds. The last part of this question is to suggest 2 improvements. The way I'd think about doing this is read the question and see what assumptions are made. So in that text on the left-hand side, you can skim through it and you'll see that it says that the balls are modeled as particles. So what's our assumption then? That the particles, how could we make the model better? We could assume that the balls have some dimensions so that they're not dimensionless. And what's another assumption? Well, in the 5th paragraph, it says that the force that is due to friction is a constant force of magnitude 12.7. So our idea to make the model better is to model it as a variable force. So if it goes quicker, there's more friction. If it goes slower, there is less friction. But there are plenty of options here that you could choose. To continue these questions, try part A and B using the same model.